Now let's go. Sean will be here shortly, I'm sure. All right, what we're going to do today, we are going to go over those 8 rules of orthographic projection. Now, I mentioned the other day, if you can't really visualize, you don't really have to. If you follow the rules that are laid out for this, because it is mathematics in essence, we're doing mathematics with a pencil, geometry, and if you follow the rules of this geometry, you really don't have to visualize anything, because geometric space is geometric space. A real object's a real object. Things have to occur in certain areas. And these are the rules that will allow you to draw anything when you can't visualize. And just so you know, I've mentioned this visualization thing several times. Just so you know, if you're not visualizing stuff like this little widget we're drawing on our first drawing, don't sweat it. Keep working on it and keep working. I don't know anybody that can visualize everything. And I've been in this industry since I was 12. I helped build my first structure. I've been in, and what, 50, heck, I don't know, over 50 now. Been in a long time. I can't visualize everything. Can't. I can visualize the stuff I've done. Like architecture, I can visualize most of it. The civil industry, building roads, these types, I can visualize that. Get me onto a machine or something, and boy, I really struggle, because that's not my background. So I've been doing it a long time, and I still can't visualize stuff. I don't know anybody that can visualize everything. I don't. It's just not the person out there. And in fact, we get into a lot of cases, like I mentioned, if you're working like a mechanical drafter for many of these food processing plants around here, they invent stuff. Nobody can visualize it because it hasn't been built. Now you go into ConAgra, now Lamb Weston. They got a machine in there that makes 1 million pounds of French fries a week. Well, where do you buy a machine like that? You don't. They invented it, they built it, they maintain it. Nobody knew what it looked like. They just started with pieces and put them together and ended up making that machine. And it's a huge machine. It takes a whole half of a building like this to do it. But there's stuff out there that nobody knows what it is. And certainly with the technology going the way it is, who knows what's coming down the road. Because we're getting smaller and smaller, and the smaller things get, the harder they are to visualize, as a general rule. Okay, so as we go through these, not all of them are things you will do every time. And in fact, some of them are things you do in the process of building a multi-view. Some of them you do to read a multi-view. Some of them you do after the fact to check your stuff. And the two I really need you to really kind of know are these two right here. Those two will build 90% of all multi-view drawings. Now, these two can't work unless you have a base set of information. So either somebody has sketched out a shape and said, I want this to be this size, this to be this size, or you've got an existing part you're trying to replicate, something of that. You need some base information to get started. Now, once you get started, then these will take over and go for you. These from 3 through 8 are kind of more analysis type of rules. So when you use 1 and 2 to build your object, then you use 3 through 8 to look at it at the end and say, yes, I did this right, or I didn't do this right. Okay. So in essence, that's the way these will work for you. Okay. But 1 and 2 you will use time and time and time again. Notice that in the definitions of 1 and 2, what do they talk about? Adjacent views, related views. Okay. So before we jump into these, what is an adjacent view? Does anybody remember that from when we defined it?
They share the same edge.
Go ahead, Misty. Just give it a try.
They share the same edge. They're like right next to
They
each
sit
other.
next to each other.
Yeah.
That's what you mean, right?
Yeah.
Yes, they sit next to each other
Share a common dimension.
and they share a common dimension. Thank you. That's an adjacent view. So this would be a top front, it would be a front right, a front left, a left rear, any views that sit next to each other. Keep in mind that glass box configuration never changes. What is a related view? What is Yes, Elise.
It's two views adjacent to the same view and share a common dimension.
Yep. So two views adjacent to the same view and share a common dimension. So in essence, this would be a top right, top left, maybe a right bottom. So on a top right, they're both adjacent to the front, right? And they both share the depth dimension. That's what makes them related. So in essence, if you know those two definitions, 1 and 2, will make a lot of sense for you. All right, what I want to do today is we're going to go through these in detail. Shouldn't take us forever, maybe 20, 30 minutes. And then I have a little exercise to help you with these also that I want to introduce after that. So let's start with this, alignment of features. Page 504, figure 1026. Let's go look at this. And we're going to use the same figure for both of the first two rules. Now, I have two definitions on each of these, just because our text has the first definition that's pretty much in there, but I had an old second text that I really like the definitions of, so I added that also. So you have two different definitions. They mean the same thing, just whatever you feel like you can remember. So, rule 1, alignment of features. Every point or feature in one view must be aligned on a parallel projector in any adjacent view. Or, a point always appears as a point in every view. What do points make up? So the base geometric unit is a point, right? If I have 2 points, I then have a line, which is an edge. That's the intersection of 2 planes. So once we have a line, then we go to faces or surfaces. So that's what I mean by a point always appears as a point in every view. If it can be located in 2 views, it may be located in every other view. So, every point. They kind of give you this idea. Now when we say parallel projectors, that's these blue hidden lines here. So if I've got this drawn, I can draw the front view. Now for me to find this top edge in my right side view, this has 4 points to it. Now you really see 2, 1 and 2, which are these 2. But that also has 2 points behind it. Now you'll see this as we go through. Now if I want to find this in the right side view, all I do is take that edge, or wherever I have a point, and I draw horizontally or perpendicular to the plane of projection, which is our fold line. Remember, there's a fold line that could be represented in here. And I'll use a phantom line to represent a fold line. Because as I unfold the box, right, this hinges out to the right side view. Okay. So my plane of projection is perpendicular here to go in. That top surface must fall on that line. It has to. Now additionally, if I'm going to do this top surface in the top view, all I do is I go, I know I got a point here, I know I got a point here, and you throw them up. They have to fall on those lines. Now you don't know where it falls on that line, but you know it's on that line. That's really law 1. You draw something, you got any point, quadrant point, center point, edge, points, whatever. You can always project that into an adjacent view with a parallel projector. Has to fall on that line. Now, where does it fall on that line? That brings us to number 2. And let me read number 2. Distances between any 2 points of a feature in related views must be equal. Must be equal. So what that means is I can now use related views to locate these dimensions. I'm going to do this a little bit different, just so you see it. So there's a fold line right here. Does everybody understand that? Any questions on what that is? Is there a fold line right here also?
Yes.
Yes, there is. Now, keep in mind, in the glass box, this object sat in the glass box and it never moved, right? We moved around the outside and edged it. Now, so that way, the dimension here is what? This way. for the top view?
Depth.
Yes, this is depth. Okay? The dimension here is what view?
Width.
No, it's not width. We're talking about the right side view. Here's the fold line for the right side view. What is that dimension?
It's depth again, isn't it?
It's depth. Those are the same dimensions. So what this in essence is saying, if I have some object that is from the fold line to here, it has to be equal over here, fold line to point. Or if you don't use fold lines, let's say I use this edge. The different distance from this edge to this edge has to be equal to the distance from this edge to this edge. Has to be. Now, how do we transmit that dimension? Well, if I use rule 1, so I've got this object and I'm getting ready to draw the top. What I would then do is I would shoot my parallel projectors, rule 1, right, for the top. Then I'm going to say, okay, well, where is this top going to be? I might draw an arbitrary line right there and say that's going to be that surface. Then I can physically measure back and find this point. So that gives me the 4 points for this surface. Now, how are we then going to transmit that over, because we know this is depth, we've got to transmit that over here. We can do it 2 ways. One, I can use a meter line, where I would then take this, shoot it over and down, shoot it over and down. That works. Or I can pull my dividers out, or a scale, and I can come in here and measure and say, well, it's right there, I know that distance. Come over here, get this line established, and measure that back, and I can find that line. The thing that you want to do is draw your front view, draw as much of any other view that I can, and you may not be able to complete the front, you may not be able to complete the right. And then you start using rules 1 and 2 to project back and forth until you get those complete. Once you have 2 views complete, you have all 3 dimensions of the object identified. You can then use that to create any and all views because you've got height, width, depth of the entire object. I don't know if that maybe confused the object or helped it, but the point being, rule 1, once you have established something, I can find any other point in any other view with a parallel projector. Where does it fall in that view? I use rule 2. I come from a related view, find the depth or the width or whatever the dimension is, and transmit it to that view. Because they have to be equal. Yes, Sharon?
When we did our drawing assignment yesterday, you had us do the math where you did the dimensions, added, subtracted them from the overall length of the paper, and then divide by 3 to get the space width. How does that, because when I did that, I had 2 for 1, and then the other one was 1.25, and if the fold lines are supposed to be equal, how does that impact that?
Good question. What's important with a fold line on the distance? Okay, so let's say we've drawn our front view. Okay, we're getting ready to produce our top and our right side, but we've drawn this one. Now I come in here and I say, you know what? Because this is a great example. Notice that this is greater than that, right? These two aren't equally spaced either way. Yours wasn't either. Okay. So what I do is I come in here off of this object and I throw a fold line in, and I just pick an arbitrary spot. All it has to do is this thing has to be parallel to my horizontal. Has to be for the glass box. Okay. Now, is this distance right here important? No. It absolutely is not important. It will never be used. Because the distance from this object to here just says, oh, it sits towards the top of the box, but there's nothing here. Now, the distance from here to here, though, is important, because this is depth. So what I then have to do is when I do this one, let me draw this in a different spot so it looks more copacetic with our picture. I'm going to draw it there. Now then I would have to come over and I would pick again an arbitrary spot for this. Now, if I come in and say, well, I'm going to make my front right here, this distance right here has to be equal to that distance. So in essence, what I'm saying is you can put the fold line wherever you want, but once you set that fold line, your related views will be the same distance from the fold line. And maybe, let me kind of maybe do this a little different. Okay. Let's say I have some object here. Let me sketch you one. Okay, so we're going to do that. This is going to be my front view. Okay. So I'm going to come in and draw my front view. And it's going to look basically like that, correct? Now, I'm going to go ahead and now build my top and right side view. The first thing I'm going to do, if I use fold lines, you don't have to use fold lines, there's other ways to do this, is I'm going to come in here and I'm just going to pick a spot. So there's my fold line, and over here I can pick any fold line up, any spot I want. Now I intentionally made the distance from here and here not equal, because it doesn't matter. I'm just picking a spot. Now what I'm then going to do is say, you know what, I'm going to then project these up, because I know there's points here that fall here and here. I know there is. They have to fall on there. Where are they going to fall? I'm going to say, you know what, I'm going to make this front edge, as I look at it from the top, which is this way. I'm going to put it, let me use the same color, go back to purple. I'm going to put it right here. That's this front edge. Then I'm going to go and measure for the back edge. It sits right there. So now I've got that surface, and I can measure that, and that is my top view right here. So, and all I did was I just came in and picked an arbitrary spot and then measured my depth, because I tried to draw as much of it as I could based on the information I had. Now, when I go to build this view, what do? I use rules 1 and 2, and that's all I have to do. So the first thing I'm going to do, what am I using? Green here? Green's my projection line. All I do is I come over and I shoot lines horizontal. Okay. Now, the distance from the object to the fold line is irrelevant, but the distance from the fold line to the object is relevant. So the distance here, I'll call it A, has to be equal over here. So where's that going to fall? So that's that edge. That's actually, yeah. So I'm going to come over and put it about right here, where this distance is A. Okay? Put it right there. Now I know that has to be that front edge. Again, I don't know where it really sits. If you do a little analysis, you're going to see it's these two lines right here. So that distance is equal. Now I can then come in and say this is going to be distance B. Okay. So I can then measure, oh wait, that's got to go to the fold line, because we're looking at the fold line analysis here. There's distance B. Then I would come to my fold line and measure that distance off and put that line where this distance right here is B. Right? Because they must be equal. Then I can do C, which would be the last one, and I'll set that one up. So now I'm kind of getting an idea where stuff at, where this distance is equal to that one, this distance is equal to that one, that distance is equal to that one. Okay. Now all I have to do is analyze the shapes, and the thing's going to end up looking like that. And it's done. Using rules 1 and 2. Now, I use fold line out. Keep in mind, you can do a meter line and not do any of those measuring. It's all projection. Because I can get the exact same thing if I come up here, do this, and do that 45-degree line, then this guy comes and projects to here. What am I doing? I'm transferring that measurement. I come to this one, project it over, it's going to hit there. Bring this one, it's going to hit there.
Does your meter line begin where your two fold lines cross?
It can, but you won't use any part of it except where the object is at. That's why when I always do a meter line, I take the closest edge, draw them up till they intersect, and then throw the 45. And then you can transfer in essence with the meter line, you're doing rule 2.
If you use the meter method, is it important for you to have the space between the fold lines equal, or does it just sort of fall into place?
The space from here, you mean?
Uh-huh.
Oh yeah, that has to be equal. It doesn't fall into place, it has to be equal. That's for you to build it. Now keep in mind, once you draw it, you can move it into your drawing and set it wherever you want. It should be in that orientation, but a lot of times we'll draw it this way, and then we end up sliding the right side view out or in, the top view up or down. We never lose that orientation with the other views, because this guy, it can only move left and right, because it's always got to line up here. Okay? This one can only move up and down, because it's always got to line up. But I will slide them, because I now have to apply dimensions in between those things, which we haven't gotten to yet. Okay? So even though I build it one way, I might display it with some slight movement to accommodate dimensions that I put in between the objects. So rule 1, a point in any view will project parallel to any other adjacent view. Rule 2, distances in related views must be equal. Like I said, you'll use that 95% of the time, will create almost everything you need. Those two. Might make a little bit of sense once we get a little more practice with it. Any other questions before we leave those two? Now, keep in mind on rule 2, let me just reiterate because we just spent a couple minutes with it. For your distances to be equal in related views, we transfer that dimension 2 ways. One, either through the use of fold lines, which are imaginary, or through the meter line method. Both of them allow you to apply rule 2. By the way, I made the comment back in CAD. There's 4 or 5 ways to do everything, and I only need you to know one. You kind of practice them, and then you come to a way that you draw, and that works effectively for you, and that's good. In this instance, you need to know the fold line method and the meter line method. You need to know them both. Now, the reason I say that is because the meter line method of applying rule 2 is the fastest and easiest way, especially with CAD. It's super fast. So you need to know that. But the meter line method will fall down on you later when we get more complicated geometric shapes, and you have to go to the fold line method to create them. So you need to know both methods. For now, I would like you to kind of stick and focus with the meter line method. When we get to a topic called auxiliary views, I'll make a big point of this, we have to go to the fold line method. That's the only way to get them done. At least that I know of, I guess I should say. All right, so there's rules 1 and 2. The rest of these are things that you want to kind of look at and see that you accomplished correctly. Number 3, true length and size, page 518. This is for normal and inclined planes. So we're looking at this figure, 10.44. Let me just read this. Features are true length or true size when the lines of sight are perpendicular to the feature. An edge line appears as a point in a plane of projection to which it is perpendicular. So we're talking about normal and inclined planes here. Remember the definition of a normal plane? Definition of a normal plane is a plane that appears true size and shape in one view as an edge in all adjacents. Okay. So in essence, this one's allowing you to identify the plane so you know how they appear. Okay. So in essence, let's just look at, how about this front surface right here? Now, do we know if this is normal or inclined or oblique? But you need more than one view to tell that. In fact, you generally need 3. This, in fact, is true size and shape. How do I know that? Because my line of sight must be perpendicular to this, because if I come to the right side view, I see that shape as an edge. Remember, these rotations are always 90. So if I'm looking at it perpendicular, or you're looking right into it, you see a true size and shape. If I turn this 90 degrees in any direction, or to any adjacent view, how does it have to appear? Go that way? Go left? How does it have to appear?
Line.
Edge, or a line. Always. Has to be. That's how we tell a normal plane. So if this guy's normal, why? There's edge, there's edge. Is this top normal? Or true size and shape? I don't know. Look at your other 2 views. I see a plane here. Where is it at down here? Right there, right? How do you see it? It's an edge. Where is it here? Technically, this one doesn't have to be there because it's a related view, not an adjacent view, but it's still an edge here. Which lines on that are true size and shape? Okay, so let's just look at a shape. Let's look at this one right here. That plane right there. Now, that is an inclined plane. We just kind of throw that out there right now.